Why could a 19th century log cabin retain heat longer than your modern apartment? And this despite the fact that the pioneers had neither mineral wool, nor plastic sheeting, nor energy-efficient windows. Their houses stood exposed to the winds of the Great Plains, covered with frost on the inside, but inside it was still warmer than you can imagine. The secret was not in the insulation, they had almost none. And it was certainly not in the technology. The settlers had nothing more sophisticated than an axe, a saw, in their own hands. The real secret lies in a fundamental principle of construction that we have almost forgotten in the age of lightweight materials, central heating, and concrete boxes. It lies in how they used the mass of the wood itself, how they made the walls work not as partitions but as giant heat accumulators. Watch this video to the end, and you will learn why a simple log wall could slowly give off heat for hours, how settlers created a thermos without a single gram of insulation, and why today this forgotten principle seems surprisingly modern again. So much so that it is returning to the architecture of the future. What if I told you that everything you believed about warm homes isn't entirely true? We are used to thinking that the warmth in a home depends solely on insulation. The entire modern construction industry is based on this. We use fiberglass, mineral wool, and foam to create a barrier between the street and the room. We measure the effectiveness of this barrier in special units. This concept is so ingrained in our minds that it seems to be the only correct one. Modern houses are built on the principle of lightness. A timber frame, covered with plasterboard on the inside and plywood on the outside, with insulation in the cavities. It's like a thermos, a light shell that simply slows down heat loss. But as soon as you turn off the heat source, such a house will cool down very quickly. The air inside loses energy, and the light walls cannot retain it. The pioneers on the American frontier had a completely different philosophy, dictated by necessity. They did not have factories for the production of insulation. Their main ally was not a barrier, but mass. They built houses not from hollow structures, but from solid, incredibly dense materials. This is the key to unlocking their thermal secret. Let's define what thermal mass is. It is the ability of a material to absorb, store, and slowly release thermal energy. Instead of simply blocking the cold, the pioneers' houses literally absorbed heat from the hearth. Dense materials such as thick logs, stone, or earth have high thermal mass. They heat up very slowly, but then cool down just as slowly. A simple analogy can be used to understand this. A modern house is like a light jacket made of synthetic materials. It keeps you warm while you are moving or while the sun is shining, but it is cold on its own. A pioneer's house is like a heavy stone block that has been heated by a fire for several hours. Even when the fire goes out, this stone will continue to radiate heat for a very long time. The sensations in such a house were completely different. The heat came not only from the stove, but also from the walls themselves. Imagine sitting in a room where the walls themselves radiate soft, radiant heat. This created a much more stable and comfortable environment, even when the fire was not burning. It was not just a warm space, it was a warm structure. This fundamental difference in approach to construction is the answer to our question. Have you ever noticed the difference in the feeling of warmth between an old brick or log house and a modern frame house? Share your observations in the comments, and don't forget to subscribe so you don't miss our next studies of life on the frontier. Are you ready to learn the truth about how people built houses literally from the ground up, using the only material available to them? On the Great Plains in places like Nebraska or Kansas, settlers faced a harsh reality. There were no dense forests here for building log cabins. All that surrounded them was an endless ocean of grass and very few trees, which grew only near rivers. Therefore, the pioneers turned to what they had in abundance, the earth itself. They began to build houses out of sod, known as soddies. These were not just miserable dugouts, but full-fledged, durable structures built using a unique technology. The material used was not just clumps of dirt, but dense layers of earth held together by thick prairie grass roots. A special plow was used for construction, which cut the sod into long strips resembling ribbons. These ribbons were then cut into bricks, about 2 to 3 feet long. The settlers laid these heavy blocks like ordinary brickwork, with the grass facing down. The wall grew slowly, row by row, reaching an impressive thickness. The thickness of the walls in such a house was its main advantage. It often reached 2 or even 3 feet. It was not just a wall, but a real earthen rampart with enormous thermal mass. This design was ideal for the climate of the plains, known for its severe blizzards in winter and scorching heat in summer. In winter, this incredible mass of earth acted as a giant battery. A small cast iron stove, fueled by dung or rare firewood, heated these thick walls for hours. The earth slowly absorbed the heat and then slowly radiated it back, maintaining a stable, albeit low, temperature in the house. Even in the strongest blizzard, it was bearable inside. In summer, the same principle worked in reverse, providing coolness. The scorching sun could not heat a 3-foot wall of earth in a single day. Inside the soddy, it remained pleasantly cool, like in a cellar. The earth served as a natural air conditioner, smoothing out daily temperature fluctuations. Of course, life in such a house was far from ideal. The walls and roofs, also made of sod, often leaked during heavy rains. Earth could fall from the ceiling. The windows were tiny so as not to weaken the structure, so it was always quite dark inside. What do you think it was like to keep the fire going and the house cozy when the walls were made of damp earth? But what if you did have trees? In the next chapter, we'll reveal the main secret of log houses, and it's not that they're just made of wood. I will reveal the best-kept secret of the old lumberjacks, which modern architecture has almost forgotten. When we imagine a log cabin, we think of romance and simplicity. But from a physics standpoint, it was an incredibly clever engineering solution. And its secret, again, is not in insulation, but in mass. Wood itself is not an outstanding insulator. The thermal conductivity of a solid log is actually quite high compared to modern insulators. But the pioneers had no choice of materials. They took what the forest gave them and compensated for quality with quantity. Instead of a thin barrier, they built a massive wall a foot thick, or even more. It was this thickness and density of the wood that played a key role. Imagine a solid wall of logs 12 inches in diameter. That's hundreds, if not thousands, of pounds of wood. Every log in that wall is a potential heat energy storage unit. The process of charging such a wall was simple but time-consuming. A fire in the fireplace or the heat from a cast iron stove radiated heat in all directions. This heat was absorbed by the surface of the logs. It took hours for the heat to slowly penetrate deep into the wood. The wall literally absorbed the energy, storing it in its structure. When night fell and the fire in the hearth died down, the process went in the opposite direction. The outside air cooled the outside of the logs, but the huge mass of heated wood inside the wall began to slowly give off its heat. This radiation was directed into the room, maintaining the temperature and preventing the house from cooling down quickly. There were different construction methods that affected efficiency. Some settlers used round logs, leaving large gaps between them. Others, more skilled craftsmen, hewn the logs, making them square or flat on both sides. Such logs fit together much more tightly, reducing the need to fill the joints. This technology was especially important in mountainous areas such as the Rocky Mountains. There, nighttime temperatures could drop very low even after a warm day. A log house heated by the sun and fire during the day could survive a frosty night by slowly releasing the accumulated heat. It was a buffer between humans and the harsh climate. Compare this to a modern frame house. Its thin drywall wall heats up immediately from the radiator, but it also cools down just as quickly. It does not store heat. A log wall is both a wall and a radiator at the same time. It smoothed out the peaks and troughs in temperature. What you are about to learn was a daily exhausting struggle for survival in these massive houses. A log house is not a monolithic structure. It consists of dozens of individual logs, and there are always gaps between them. No matter how massive and heat-retaining a wall was, all its effectiveness was negated if icy winds penetrated the house through these gaps. This problem was the Achilles heel of log construction. Filling these gaps, known as chinking, was as important a process as building the walls themselves. The quality of this work directly determined whether a family would survive the winter. It was a never-ending battle against the elements. The materials for caulking were simple and taken literally from underfoot. Most often it was a mixture of clay, sand, water, and some binding material, such as dry grass or moss. In some regions where lime was available, a more durable lime mortar was made. But for most pioneers, it was just mud. The process was laborious. This mixture had to be tightly packed into the gaps between the logs, both outside and inside. Often, wood chips or stones were first inserted into the large gaps, and only then were they filled with the clay mixture. It was dirty, painstaking work that required patience. The biggest problem was that the house lived its own life. The wood constantly dried out, expanded, and settled. The logs changed their geometry depending on humidity and temperature. Because of this, the clay putty cracked, crumbled, and fell out, opening the way for drafts. Therefore, caulking was not a one-time job. Every fall before the cold weather set in, the whole family took part in the repairs. They walked around the house, inspecting every seam, and re-caulked all the cracks. Postponing this work meant condemning themselves to suffering during the winter months. Even a perfectly caulked house was not airtight by modern standards. There were always small gaps through which cold air seeped. This created constant air movement. The warm stove drew cold air through the gaps, creating noticeable drafts near the floor. That is why, despite the massive warm walls, the pioneers still needed a constant source of fire. The thermal mass could retain heat, but it could not compensate for the loss from drafts. It was a constant balance between the accumulation of energy in the walls and its leakage through the cracks. Can you imagine how much work it took just to maintain the integrity of these walls? But what if you had neither logs nor sod? In the next chapter, we'll head to the southwest to learn the secrets of houses built from the desert itself. Now we'll move to a completely different region of the frontier, the arid Southwest. In Arizona and New Mexico, settlers faced different challenges, a shortage of not only trees but also sod. However, there was an abundance of clay, sand, and sun. They borrowed a construction technique that local tribes, such as the Pueblo, had been using for thousands of years. This is adobe, a construction method using unfired clay bricks. This is perhaps the most striking example of the use of thermal mass in architecture. The bricks were made from a mixture of clay, sand, water, and straw, which was used as a reinforcing material. This mixture was molded and left to dry in the scorching sun. The walls made of these bricks were incredibly thick, from 2 to 3 feet. As in the case of turf houses, it was not just a wall, but a massive barrier. But in the desert, this mass had a dual purpose. It had to protect not only from the night cold, but also from the daytime heat. The principle behind an adobe wall is pure energy management. During the day, when the desert sun heated the air, its rays fell on the thick wall. But it took many hours for the clay to warm up. While the heat slowly moved toward the inner surface, the inside of the house remained cool. In the evening, when the sun set and the temperature in the desert dropped sharply, sometimes to almost zero, the opposite happened. The heat wave accumulated by the wall during the day finally reached the inner surface. The massive wall began to radiate this heat into the house, warming its inhabitants throughout the night. It was an ingenious passive heating and cooling system that worked without a single moving part. It used only the properties of the material and the daily cycle of the sun. Settlers who arrived in the Southwest quickly appreciated and adopted this technology. The roofs of these houses were also massive. A layer of branches was laid on thick wooden beams called vigas, and a thick layer of clay was laid on top of that. This roof also acted as a thermal buffer, protecting from the sun and retaining heat at night. Of course, this technology had its weaknesses. Adobe is vulnerable to water. Heavy rain could wash away the walls, so they had to be regularly coated with a fresh layer of clay. This was as much a mandatory annual maintenance task as caulking log houses. Are you ready for the shocking truth about how useless and even harmful the famous pioneer fireplaces were? We are used to seeing huge open hearths in movies as a symbol of comfort, but from a heating perspective, it was an incredibly wasteful and inefficient device. Most early settlers built these types of fireplaces, often out of stone or clay. The problem was that up to 90% of the heat generated by burning wood literally went up the chimney. The fire burned brightly, but it mainly heated the street, not the house. Moreover, such a fireplace acted as a powerful pump, drawing warm air out of the room. To maintain combustion, it required a constant supply of oxygen. It sucked this oxygen in from all the cracks in the house, creating icy drafts. People could warm their faces by the fire while their backs froze. Why were they built? First, it was a tradition that came from Europe. Second, the fireplace was needed not only for heat, but also for cooking and lighting. It was a multifunctional center of the house, despite its shortcomings. And most importantly, it radiated heat. It was this radiation, not hot air, that was important for houses with thermal mass. Direct radiation from the flames was absorbed by the stone hearth, floor, and massive walls opposite. The fireplace slowly but surely charged the mass of the house, which then gave off heat. A real revolution in heating on the frontier came with the advent of cast iron stoves. Stoves, such as the Franklin or the simple potbelly stove, were many times more efficient than an open fireplace. They were relatively airtight and allowed the air supply to be controlled, slowing down combustion. A cast iron stove radiated heat in all directions, 360 degrees. It heated not only the wall behind it, but also the entire volume of air in the room. The metal quickly heated up and became a powerful source of radiant heat, which was effectively absorbed by the walls. With the advent of stoves, homes became much warmer. Wood consumption decreased dramatically, as it now burned much more efficiently. The stove could be fed for the night by placing large logs inside and covering the damper. It would then switch to a slow smoldering mode, maintaining heat until morning. Do you think it was difficult to control such a fire all night long, so that it would not go out and burn down the house? But even the best fire is useless if the heat escapes. In the next chapter, you will learn what architectural tricks settlers used to literally lock the heat inside. If the walls of a house were its heat radiator, then the windows and doors were the main sources of heat loss. Pioneers instinctively understood what modern engineers calculate on calculators. Every opening in a wall is a hole in your defense against the cold. Therefore, frontier architecture was an architecture of minimizing losses. The most vulnerable spot was the glass. In the 19th century, there were no double-glazed windows. Glass was thin, expensive, and conducted heat almost as well as metal. Each window was, in essence, a radiator working in reverse. It sucked heat out of the house. Therefore, settlers made windows as small as possible. Often, there were only one or two tiny windows in the entire hut, barely letting in any light. This was not a whim or a lack of aesthetic taste, but a harsh necessity. The choice was between light and heat, and in winter, heat always won. In the early stages of frontier settlement, there was often no glass at all. Instead, the openings were covered with oiled paper or thinly tanned leather. These materials let in a little dim light, but they were no better than glass for insulation, and in some cases even worse. They only protected against the wind. An integral part of any window was massive wooden shutters. They were not for decoration. At night or during a blizzard, the shutters were closed tightly, creating an additional, albeit leaky, air barrier. They were similar to modern curtains, only much stronger and rougher. The same applied to doors. Houses rarely had more than one entrance. Doors were made of thick, solid planks and were fitted as tightly as possible to the doorframe. But even so, there were inevitably gaps around the perimeter of the door through which the wind howled. To combat this, a strip of fabric or skin was often nailed to the bottom of the door. At night, the gaps at the threshold could be plugged with rags. Sometimes a small vestibule or porch was built, an unheated room in front of the entrance. This allowed people to enter the house without letting the icy air into the living room. We have talked a lot about walls, but an equally important battle for warmth was taking place under the settlers' feet. The construction of the floor had a fundamental impact on how warm the house would be. Here, too, the pioneers used the earth to their advantage, although initially unconsciously. The earliest and simplest huts often had no floor other than the beaten earth. This may seem primitive, but from a heat perspective, it was not the worst solution. The earth beneath the house, being below the frost line, has a stable, positive temperature all year round. This earthen floor essentially connected the house to the planet's giant geothermal mass. The ground beneath their feet never cooled to the outside temperature. It was always a source of weak but constant heat, or at least it was not a source of freezing cold. The advent of wooden floors was a huge step forward in terms of hygiene and comfort. It was no longer necessary to walk on mud. However, this created a new engineering problem. Plank floors raised the living space above the ground, creating a cold, unventilated underground space beneath it. This crawl space became a trap for cold air. The icy wind penetrated under the house and cooled the thin floorboards from below. As a result, the floor became the coldest surface in the house. Heat escaped directly through the cracks in the boards. The pioneers quickly found a solution to this problem. In the fall, they performed a procedure known as banking. They raked or piled earth, sod, straw, or any other materials onto the foundation of the house from the outside. This embankment blocked the wind and prevented it from blowing under the floor. More substantial houses had stone foundations and full basements or cellars. Cellars, which went deep into the ground, also took advantage of the stable temperature of the earth. They served not only to store supplies, but also as a buffer zone that prevented the house from freezing from below. Massive walls and small windows were only half of the equation. The other half was constant, exhausting human labor. 19th century houses did not stay warm on their own, but because the people in them never stopped working to maintain the heat. The main task that determined the daily routine was fuel preparation. Cast iron stoves or fireplaces consumed enormous amounts of wood. Families had to prepare and chop a huge supply of firewood for the entire winter. This work was carried out throughout the summer and fall. During the cold season, the fire required round-the-clock attention. It could not simply be turned on and off. Someone had to constantly add wood, monitor the draft, and rake out the ashes. It was tireless work. The fire was not simply left on overnight. There was a whole procedure for laying or banking the fire. The largest logs were placed in the stove and then tightly covered with ashes, almost blocking the oxygen supply. In this mode, the fire did not burn but smoldered, giving off a minimum of heat but not going out until morning. The heat from cooking played a huge role. The stove often burned all day because breakfast, lunch, and dinner were cooked on it. This heat also went to charge the thermal mass of the house. In winter, the kitchen was the warmest place, and the whole life of the family often centered around it. Now that we know all this, we can return to our original question. Why does a lightweight modern house, built according to all the rules of thermal insulation, cool down so quickly? The answer lies in the efficiency paradox. We have learned to heat air very quickly, but we have forgotten how to store heat. A modern heating system is an active system. Your thermostat detects a drop in temperature, and the boiler immediately turns on, pumping hot air into the room. The air warms up in minutes, but this air has almost no mass, and it cools down just as quickly. The walls of a modern house, consisting of drywall and insulation, play almost no role in this process. They only slow down heat loss, but remain cold themselves. They do not store energy. Heat in such a house is, in essence, simply heated gas. That is why, as soon as you turn off the heating, the temperature drops sharply. The house has no heat reserve. The entire system depends on the constant and uninterrupted operation of the heat source. It is efficient but fragile. The pioneer's house was the complete opposite. It was inefficient at heating. It took hours to warm up, but it was incredibly stable thanks to its mass. It was like a heavy freight train, difficult to get going, but then almost impossible to stop. This thermal inertia is the secret. A log or earthen wall, heated to a depth, became an independent source of heat. It smoothed out temperature fluctuations. Even if the fire went out, the walls continued to heat the room for several more hours. We can see that the secret of the pioneers' warm homes was not some mythical insulation, but a fundamental physical principle: thermal mass. Whether using thick logs, earthen walls, or adobe bricks, the settlers intuitively built homes that functioned like giant radiators. What other aspects of life and survival on the American frontier would you like to see in our future videos? Perhaps you are interested in water extraction, food preservation, or the peculiarities of traveling in a wagon? Suggest your topics in the comments. And of course, don't forget to subscribe to our channel so you don't miss new research on how people actually lived on the frontier of civilization.